Hello everyone, welcome to this video. In this video, I'm going to discuss about quantum mechanics. Now you might be wondering that we started the course as quantum computation, but then how suddenly quantum mechanics is in the playlist? That also is the first lecture, right? So just understand one thing, that if I'm using this as the first lecture, that means somewhere this forms as the basis of quantum computation, okay? So how is it that I'm going to discuss in this lecture? Now here are a few points that I have written. So the first point is, first of all, about quantum computation. As such, detailed video I have not brought yet, where I am explaining like the definition and the basic concept. I will be doing that in upcoming lectures. So, but before that, one brief idea if I give, quantum computation and quantum information. First of all, these are the two things, these two terms goes always kind of hand in hand, okay? And in one line, if I have to summarize that what is this quantum computation all about, what is quantum information all about, then it is the study of the information processing task. Okay, end of the day, this is the main agenda of quantum computation. That is, we are going to have a lot of information and we have to process that. That is the main task. Okay. Now the thing is, if we talk about classical computation, even there, classical computation is also the study of information processing task only. In classical computers also, what we do, we get a lot of data, we get a lot of information, and end of the day we process it. And whatever is the result, that result we use for various applications, right? But the main task is information processing. So this is one similarity between classical computation and quantum computation, right? Now the next question is, what is the difference then? So the difference is, quantum computation accomplishes, because this is the main question, that okay, we are going to process information, that is fine, but how we are going to do it? How we are going to accomplish it, right? So this is the answer, that we are going to accomplish this using quantum mechanical systems in quantum computation. And that is how the name also has been derived from here. Okay. So I guess this is the first time that you are encountering this term in my course, that is quantum mechanical system, right? Now what is this system and exactly how it is used, how it is utilized for processing information, that is definitely not possible to explain in this one lecture, and our entire course is going to be about this only, okay? But then that is how it forms the basis for quantum computation, okay? So this was the first point. Now the next point is, there are certain fields, and as you can see the names already, majorly there are 4 fields that have contributed to the fundamental ideas of quantum computation and quantum information. Okay. So what are those 4 fields? First one is definitely quantum mechanics, and this is the reason that I have made this video. And in this lecture, we are going to discuss this in detail. Okay. So quantum mechanics is the basis. Now how it is, we will see in some minutes. Next is computer science. So computer science also have contributed to the fundamental ideas. Okay. So how is it so? Because again, whatever computation, whatever theories we have studied in computer science, we have driven the basic idea, the patterns, okay, the motivation from computer science itself. One example I can give you, like in computer science, we study something that is called logic gates. Okay, I hope you have the idea. Even if you don't, it is not a problem, because in upcoming lectures, I'm going to come up with this concept, logic gates. But in computer science, we have something like this. Now, similar gates, we also study in quantum computation as well. Those are known as quantum gates. Okay, quantum gates. So this idea of quantum gates has been derived from logic gates itself. Right? So this logic gate is forming the base on top of which some quantum mechanical theories have been applied, and we have something called quantum gates. So that is how computer science has contributed. This is one such example, but there are a lot more that we will study in upcoming lectures. But this is how computer science have contributed to this field. Next is information theory. As I told, quantum information we have, and our main task is to process information. So for processing information also a lot of theories are there which are implemented in quantum computers. And lastly, we have cryptography as well. So this field also has contributed to quantum computation a lot. So our entire course is going to be a combination of all these concepts. Okay. But particularly in this lecture, I am going to discuss only about quantum mechanics. So let us start with this now. So the best way to understand quantum mechanics is, first of all, to understand both of these terms separately. That is, what is quantum and what is mechanics. Once we understand these two terms separately, we will automatically get a brief idea that what quantum mechanics is in a merged manner, right? So let us understand both the terms individually first. So the first term that we have is quanta, singular is quantum actually. So this is the smallest indivisible unit of a physical property. Physical properties like energy or light. Now about energy and light, we all have brief idea, right? We already study these things in our high school. So these are some physical properties that we have around us, right? So what is the smallest unit of these physical properties? So that smallest unit is known as quantum. Okay, like for example, you must have studied something known as photons. Okay, even if you not, it is not much problem. But generally we study this in our high school and all. So we have studied something called photons, right? So this is one such example. So whatever is the smallest unit, that is known as quantum. Okay. The next word is mechanics. So mechanics is the area of physics concerned with the relationships between force, matter, and motion among physical objects. Okay, so in mechanics, what do we study? We study about matter, right? So matter is there. Now, if matter is there, definitely energy we have. Matter, energy, they are kind of related, right? So I'm not getting into too much physics as of now, but this is what we have, we know, right? So we have matter, we have energy. Now we apply force on matter, right? And it creates a motion, right? So how these things are related, that study is known as mechanics. So you might also know like something is known as Newton's law of motion, right? Newton's law of motion. So here we study about these things only, that how matter is there. Like the second law of motion states that force is equal to mass into acceleration, right? So this is what? This is basically finding the relationship between force, mass, acceleration and all of that. So this study we have done, right? So this study itself is known as mechanics. Also, mechanics deals with bodies that are either at rest or are moving with velocities significantly less than the speed of light. Okay, so majorly what we study about that the object is in rest or it is in motion, and related to that, whatever properties are there, whatever theories are there, whatever phenomena is there, this study is known as mechanics. Okay, so now at this point we are having the idea what is the meaning of quantum, what is the meaning of mechanics. So now if I use the term together, that is quantum mechanics. So now what do you understand by this? Okay, so quantum was the smallest unit, smallest unit. Okay, quantum is the smallest unit. And what is mechanics? What did we understand? That here generally we talk about the motion. Okay, so that means what is quantum mechanics? Quantum mechanics is the study of motion at smallest level, at, you can say, atomic and subatomic levels. How these smallest units interact, how they move, when any force is applied on them, how they behave, what impact it creates. So all of this entire study is known as quantum mechanics. Okay. And from here, whatever idea, whatever knowledge we will get, this is something that we utilize in quantum computation. Okay. Because the thing is, any type of computation it is, we have to have some fundamental unit, right? We need to have some fundamental unit. Like for example, in classical computing, what is the fundamental unit? The binary digits that we call as bits, right? So bits are there. Now bits are having certain properties. That is, a bit can be either 0 or 1, right? So on bits, what kind of computation we can do, what operations we can do, right? What results it generates. So all of that is a complete study. Okay. Now same thing we have to do here also. In quantum computation, we have to know that what is the fundamental unit. And that fundamental unit, what are the powers of that? What computations it can do, right? And how it can generate information, how it can process information, all of that. So that is why quantum mechanics is so important. Understanding this is so important because quantum computation is nothing but implementation of this quantum mechanics. Okay, in a way, in a very summarized manner, I'm telling this. There's a lot more, okay, but this is what basically it is. So I explained it from my side, but let us also see a proper definition of quantum mechanics. So it is the branch of physics that studies the behavior of matter and energy at atomic and subatomic level. This is what I told you, right? So how matter, energy, all this behave at atomic and subatomic level, that is the fundamental unit level, that is what is quantum mechanics. So it describes how things behave in the very small world, which is quite different from how we experience the world in our everyday lives. Okay, because we understand generally that how force is acting on us, maybe the same thing is happening at atomic level also, but that is not always the case. The behavior at atomic and subatomic level is quite different. So how it is quite different and how we can utilize that, that is the entire course is about, right? So we will study that. But I hope now you got a brief idea about quantum mechanics. I also tried to relate it to quantum computation as well, but there's a little more to it. And that little more we can understand only when we understand the mathematical aspect of this quantum mechanics. Okay, so now let us do it. So this is now the mathematical aspect. So mathematically, how we can understand quantum mechanics? Till now, whatever we did, that is in general physics term. But mathematically, how we can define? So mathematically, quantum mechanics is a mathematical framework or set of rules for the construction of physical theories. Okay, there are certain physical theories around us. Okay, so no matter what is the physical theory we are talking about, all of them works under a certain mathematical framework, a certain set of rules. Quantum mechanics sets that rule. Okay, now this line might seem very, kind of, it is like a umbrella definition kind of thing, right? But internally there's a lot more to discover, which we will be doing in upcoming lectures. But this is what it is. Quantum mechanics is like a framework, and within that framework, certain physical theories work. And those certain physical theories we are going to utilize and do computation using that. And that becomes our quantum computation. Okay. So this, to understand this relationship, actually, I have taken a good example from a book actually. And all of these resources I have mentioned in the description. So you can see from there. Okay. So the relationship of quantum mechanics, I'm writing in short here, to specific physical theories. Okay, as I told you, multiple physical theories are there. Here one example is, let us say, quantum electrodynamics. This is one particular physical theory. Okay, so what is that? Quantum electrodynamic. Right. So we have quantum mechanics and we have quantum electrodynamic. Now what is the relationship between them? How they are related? Okay. This relationship we can understand with one kind of analogy. The analogy that is easier for us to understand because that is related to classical computing. Okay, so the analogy is of operating system and application software. So let us understand that. So in classical computing, if I talk about, we have something called operating system. And this operating system, brief idea everyone is having, right? It is a system level software that is used for process management, resource management and all, right? And then we have some specific application software. Okay, so these specific application softwares are used for some specific task. Let us say we have Excel related work or PowerPoint, right? These are different application softwares. Now, so what is the relationship between operating system and application software? What this operating system does is it sets certain rules. Okay, specifically if I talk about its role, there's a lot, like I listed process management, resource management and a lot, right? But in general, if I talk, then operating system sets certain rules. And these application software does its task, but under that set of rules. Okay, so that is the relationship. We know that OS is like the manager. OS is like the manager. So the role of manager is to set certain rules, to divide the task, right? To monitor everything. That is the role of a manager. And within that, the employees have to work. That is the kind of relationship, right? Now the same thing happens between quantum mechanics and quantum electrodynamics. So in mechanics, we set certain rules. Okay, and within that framework, within that set of rules, the different physical theories work. One such physical theory is quantum electrodynamics. This is just an example, but there's a lot more. So this is how they are related. Okay, so now how it is related to quantum computation. Now quantum computation, when I'm talking about, it is also going to use a lot of physical theories. Okay, it is going to use a lot of physical theories. Right? So all these physical theories, as we talked, all these physical theories are going to work under certain framework and a set of rules. And that is set by quantum mechanics. Right? So this is how quantum computation is becoming dependent on mechanics. This is the relationship between them. And that is the reason why we should understand quantum mechanics properly in detail. Once we understand this, the framework, then within that we can do quantum computation. Okay. So this is the overall idea. This is the relationship. Now again, when I said that we have to understand quantum mechanics in detail, it does not mean that first of all we need to study quantum mechanics completely and then, because that is not possible. Okay, not even required as such. Just you should have the brief idea that quantum mechanics is the basis of quantum computation. After this, whatever different concepts I will be bringing, right? So there I will, wherever it is required, I will mention that how this concept has been derived from quantum computation and how we are implementing it. It has been derived from quantum mechanics and how we are implementing in quantum computation. Okay. So all of that we will be doing. A lot is still remaining that we need to discover. This is just the beginning, but I hope that you got one brief idea about quantum mechanics. Okay. Now, whatever resources I have used for this lecture, I have mentioned everything in the description, so you can go and visit them. And also the queries and the suggestions are welcomed, so you can put your queries and suggestions in the comment section. So with this, I'm ending this lecture. Thank you.